This is section 4.6 in your book. We're going to go through some numerical integration, and we're going to learn about using the trapezoid rule. We're going to use that when there are functions that just don't have good sets of antiderivative. So kind of listed some of those down here. Got the cube root of 1 minus x, square root of x, cosine of x over x, square root of 1 minus x cubed, and sine of x squared. Just some more challenging functions. The trapezoid rule, kind of similar to how we did the left and right hand Riemann sums, where we were taking a bunch of rectangles and adding up the different areas of all the rectangles to get the total. The trapezoid rule is a better approximation. If you can look at the picture here that's on the notes, we can actually, get closer to being under that curve without going over too much or being under. So it's just a closer approximation for us to be able to calculate the area under a curve. So instead of banking a bunch of rectangles, we are going to add a bunch of trapezoids up. Alright, so if you remember under the graph here of the trapezoid, just basic geometry, to find the area of a trapezoid we had to take base 1 plus base 2 divided by 2 times the height. Okay, so it looks a little backwards on this way if you kind of turn your head sideways or not and look at the picture. Alright, base 1 and base 2 are actually the short height and the tall height of the trapezoid there, and the height of the trapezoid for us is actually its change in x distance. Alright, so if we kind of turn that picture on the side, that's really how we're going to equate everything. So when we set this up, we have the area of the ith trapezoid. The formula for that is going to be f of xi minus 1 plus f of xi divided by 2 multiplied by the change, which is b minus a over n. Okay, and n is kind of like when we did rectangles. N is going to be the number of iterations that we're going to do, or the number of trapezoids that we're going to take in this case. So we're going to take a look at theorem 4.7. It's the trapezoid rule. So we're going to say f is going to be continuous on the interval from a to b. So when we write that out as an integral, it's a to b f of x dx. And to solve that integral, we're going to use this summation formula type expansion here. Alright, we're going to have b minus a over 2n times everything that's in the quantity. We're going to evaluate the function at each and every single one of those points. So we're going to evaluate the function at 0, or x0, x1, x2, so on and so forth, for however many iterations we're going to take. Now, also looking at this, there's coefficients on all the middle terms. This is important for the trapezoid rule. The first and the last term that we evaluate do not have a coefficient. All of the terms in the middle of the first and last two will have a coefficient of 2. That'll make probably more sense as we do a numerical problem here. So let's look at example 1. We're going to use the trapezoid rule here to solve this integral. So we're going to go from 0 to pi of sine of x dx, and we want to do the results when n is 4 and n is 8. So we're going to do two separate parts for this problem here so you guys can kind of see what's going on. Alright, so the solution, just analyzing the graph. Okay, I kind of overemphasized the trapezoid piece in this sketch so you kind of see what's going on. Alright, the curve piece is y equals sine of x, and it's from 0 to pi, so it's just a small snippet of the graph of sine. Alright, a is 0, b is pi. Those are the limits, the upper and lower limit on our integral. We're going to do the first one when n is 4. So the first step to all of these is just like when we did the left and right hand sum. We are going to find delta x. So b minus a divided by n, so pi minus 0 divided by 4 is pi over 4. Now we have to find all the increments that we are going to evaluate the function at, because we're going to go from 0 to pi, but we have to find all the different spots that we're going to evaluate so that we have all the base 1s and base 2s as we do this. So starting at 0, we're going to use delta x each time. So I'm going to do 0 plus pi over 4 because that's my delta x. So I'm going to evaluate it at pi over 4. And then I'm going to take pi over 4 and add pi over 4. That's going to give me pi over 2. So we're going to evaluate at pi over 2. I'm going to take pi over 2 and add pi over 4. That's going to get me to 3 pi over 4. So we're going to evaluate at 3 pi over 4. And then I'm going to take 3 pi over 4 plus pi over 4 to get pi. How do I know when to stop? When I'm at the end of the interval. So the first value I evaluate is the beginning of the interval, which is 0. The last value that I evaluate is the end of the interval, which is pi, and then we had to calculate pi over 4, pi over 2, and 3 pi over 4 in between. This is an important step, and it's one that you need to make sure that you understand how to do. So look at the graph. I labeled all the points that we are going to evaluate, except for 0. I forgot to put 0 on there. But we are going to evaluate 0, pi over 4, pi over 2, 3 pi over 4, and pi. Next is the important part, and we're going to evaluate them in that order so we know where to put the coefficients. So we're going to put this into theorem 4.17. So we're going to take the integral from 0 to pi of sine of pi x, or sine of x dx. I shouldn't say sine of pi, I should say sine of x there, dx. So I got an error on my notes there, so please correct that accordingly, sine of x dx. Okay. Plugging into b minus a over 2n. So that's going to be pi minus 0 over 2 times 4. We're going to do 4 in this case. Now, notice as we substitute in, it says f of 0, f of pi over 4, f of pi over 2, f of 3 pi over 4, f of pi. Those are all the values that we calculated, and we had the first part of the interval and the last part of the interval. So notice we're going to plug each one of those values into the function. The function is sine of x. So we're going to evaluate it thus. Also, pay attention as we do this expansion. The first term and the last term in that expansion do not have a coefficient of 2. This is important. You have to stick with that nomenclature, and that's the way it's done. All the terms in between the first and the last term must have that coefficient of 2. It's not a part of the function, it's a part of the theorem. Okay? So, now we evaluate at each one of those terms. So I simplified the pi minus 0 over 2 times 4 is pi over 8. Sine of 0 is 0. 2 times sine of pi over 4 is square root of 2. 2 times sine of pi over 2 is 2 times 1, which is 2. And then we have 2 times sine of 3 pi over 4, which is square root of 2. And sine of pi is 0. Now we add all these together and multiply by pi over 8. And you should get 1.896. So, we're going to redo all of this for n equals 8. The problem up here asked us to do it when n was 4 and when n was 8. So we're going to go down. So hopefully we gain an understanding of when n is 4. And let's go down. We're going to do the same exact problem here when n is 8. So notice what's going on here. We got 1, 2, 3, 4, 5, 6, 7, 8 trapezoids now instead of 4. So I've drawn the picture to kind of give you an idea of what's going on. Since we're doing this problem using n equals 8, you have to find the new delta x. Same procedure for finding delta x, b minus a over n. Okay, so it's pi minus 0 over 8. So we're going to get pi over 8 for that. Then we have to find all the different values that we need to evaluate. So you can see I've drawn them on the graph here. We're still taking that snippet from 0 to pi of sine of x. But remember, starting at 0, we are going to evaluate 0, and we're going to stop at pi. That's the last point we evaluate. We're going to find all the different points in between. So the way we're going to do that is we're going to take 0 plus pi over 8. That's going to give me pi over 8, so that's the first value, or the second value technically that we're going to evaluate. I'm going to take pi over 8 plus pi over 8. That's going to give me 2 pi over 8, which is going to tell me pi over 4. I'm going to take pi over 4 plus pi over 8, get 3 pi over 8. Then I'm going to take 3 pi over 8 plus pi over 8. You guys kind of get the gist here. Alright, the last term that you calculate, you're going to add pi over 8 to it each time. So really where we're going is we're going in pi over 8 intervals, but we're looking for what that value is. So this is real similar to the n equal 4. I don't need to walk you through step by step on this one. the part we got to pay attention to. Okay, we're going to substitute all of these values in to the function using theorem 4.17 or 4.17. So b minus a over 2n, so that's going to give us pi minus 0 divided by 2 times 8 this time. And I've written it all out, kind of scrunched it in down here at the end. Once again, pay attention. The first term and the last term does not have a 2 in front of it, but all the middle terms that we evaluate all have a 2 in front of them. Every single one that you do. So only the first term and the last term do not have a 2 in front. The remaining terms all will have a 2 in front of them as you evaluate them. So make sure that you do that. That's very, very, very important. And remember, this is all for the trapezoid rule. So we're going to evaluate the function. The function is sine of x. So we're going to substitute in every single one of those values in for sine of x. So sine of 0 is 0. Then we have 2 times sine of pi over 8. Make sure you're in radians. That gets us 0.765. Then we have 2 times sine of pi over 4, which is 1.41. Then we have 2 times sine of 3 pi over 8. We get 1.84. We have 2 times sine of pi over 2, which is 2. We have 2 times sine of 5 pi over 8, okay, which is 1.84. We have 2 times 3 pi over 4, which is 1.41. We have 2 times sine of pi over 8, which is 0.765, and we have sine of pi, which is 0. This one in particular, notice how it goes from 0, increases up to 2, and then decreases evenly down to 0. Not every single one of those is going to have this special of a pattern. Okay, so don't think that that works for every single problem we do. It's working for this problem, but not for all of them. If you add all those up and multiply by pi over 16, you should approximately get 1.969. Now, the number of decimal places that you use changes the accuracy of the number. Since I've only really used kind of between 2 and 3 decimal places here, my number's not as accurate. If I carried those out to 5 or 6 different places, I would have a much more accurate number. Because the goal is kind of compare the two. So when n equals 8, we're at 1.969, okay? And then over here when n was 4, we were at 1.896. So we should be getting closer and closer to the true value with the more number of iterations that we take, so if we increase n. Alright, so that's using the trapezoid rule for the most part. Now, we're going to use the trapezoid rule here on a basic one. We're going to approximate the definite integral here from 0 to 2 of x squared dx when n equals 4. Doing this one because it's similar to your homework assignment, so hopefully you can kind of go through step by step and compare and see what's going on. Same exact rules apply. Nothing changes. We're just going to use the trapezoid rule to approximate this integral, and we're going to do it when n equals 4. So we're going to have 4 trapezoids. First step, find delta x. So b minus a over n, so 2 minus 0 over 4, ends up yielding 1/2. We have to find the intervals that we're going to evaluate. So we're going to start at 0 because that's the lower limit on our integrands. We're going to take 0 plus 1/2. That gives us 1/2. Then we have to take 1/2 plus 1/2. That gives us 1. Then we have to take 1 plus 1/2, which gives us 3 over 2, right? And then we get 3 over 2 plus 1/2, which gives us 2. So we're going to evaluate the trapezoid rule at 0, 1/2, 1, 3/2, and 2. Very simple on this problem here. So just remember, when we're doing step 2 here, finding the intervals, okay, we're just really adding delta x each time to our answer. Alright, now we're going to plug into 4.17, and we're going to plug into the actual function. Remember, the function in this case, if we go up, is x squared. Okay, so we have our leading piece, b minus a over 2 times n, so that's going to yield 1/4 for us. And then here, I have to take 0 squared plus, one more thing I want to iterate before I go through all this. Notice the first term 0 and the last term 2. The 0 squared and the 2 squared, those do not have leading coefficients of 2. the three middle terms do have the leading coefficients of 2. You need to make sure that you add those in when we're doing the trapezoid rule. So 0 squared plus 2 times is 0, right? Plus 2 times 1/2 squared gives us 2/4, plus 2 times 1 squared gives us 2, plus 2 times 3/2 squared gives us 9/2, plus 2 squared gives us 4. Okay? So when you add all these up, 0 plus 2/4 plus 2 plus 9/2 plus 4, you get 11. And then we multiply by that width change in front, so that's 1/4. So 1/4 times 11 is 11/4, or you could get 2.75. So that's similar to homework problem number 1. So that's the first part of 4.6, is understanding and learning how to use the trapezoid rule. I didn't give you a ton of problems on this. I think it's relatively easy, but they will be on your test, they will be on your final, so make sure that you know how to do this. So this is similar to homework problem 1. The next part of lecture for 4.6 is going to cover Simpson's rule. So if you have any questions like this, as always, go ahead and shoot me an email. I have the notes uploaded to the website as well, so you can grab the PDF of them.